Covalent compounds are known as molecules. They share electrons. They are not made of ions. They are made of elements that are sharing electrons. And this shared pair of electrons is a lot of times drawn as a line. This line is a covalent bond. These are single bonds that I've drawn here. It's a pair of electrons, two shared electrons. You could have a double bond, which would be 4 electrons being shared, 2 pairs. You can also have a triple bond, which is 6 electrons or 3 pairs of electrons being shared. For a covalent compound, the formula is the number of each element that is in the molecule. So it is the molecular formula. So for this molecule, it has 2 carbons and 6 hydrogens in each molecule. So the compound formula would be C2H6. That is what's in the molecule. So that's the molecular formula. For a covalent compound, the empirical formula could be different because for C2H6, the simplest ratio is actually CH3. So the empirical formula for this compound would be CH3. It's different from the compound formula. For ionic compounds, the empirical and compound formula will be the same. Here is a water molecule over here. There is 1 oxygen and 2 hydrogens in the water molecule. H2O is the compound formula. It is the molecular formula. And for water, it happens to also be the simplest ratio. So the empirical formula is the same as the molecular formula for the water molecule. So the empirical formula could be the same as the molecular formula, but it could be different in a covalent compound. So these lines that represent covalent bonds, shared pairs of electrons, can be evenly shared. So they could be nonpolar covalent bonds. So they're shared evenly, like the bond between 2 chlorine atoms. It's shared evenly. Neither chlorine can pull harder on the electrons, and so the electrons spend an even amount of time around both of those chlorine atoms. Or a bond can be uneven. It can be polar, meaning that there is a dipole. There's a more positive end and a more negative end. So there's a dipole to this shared pair of electrons. It's not shared evenly. The chlorine pulls more strongly on the electrons than the hydrogen does. And so they spend more time around the chlorine than they do around the hydrogen. And so that gives this end of the molecule a little bit of a negative end. So if we visualize this molecule as kind of like an oval, this end of the oval would be a little bit more negative, and this end of the oval would be a little bit more positive. These little deltas represent a partial negative charge and a partial positive charge. It's not an ionic compound. It's not a full negative and a full positive charge, but it is partially negative and partially positive. Another representation is to have an arrow showing where the electrons are headed or where they spend more of their time. And you could put a little plus on the opposite end to show that there's some electron deficiency at the other end there. Chlorine is more electronegative than hydrogen. It pulls the electrons towards itself. So we have kind of a darker color here to show that there's more electron density here. The electrons are spending more of their time here. And this is a little bit faded in comparison. There's less electron density here. You can draw an arrow pointing towards where the electrons are more likely to be found, and then with a little plus on the other end to show that there's an absence of electrons here. So this is also a very common way to show it. Another way is to use this lowercase delta, the Greek lowercase d for delta, meaning that there's a little bit of something. So there's a little bit of positive here and a little bit of negative here, not a full +1 or -1 charge, but a little bit of positivity on this end, a little bit of negativity on this end of the bond. So we call this a partial positive charge or partial negative charge. How do we know how strongly a certain element is going to pull on the electrons? That property is something referred to as electronegativity. It increases going up the periodic table and to the right of the periodic table. It is not the same as electron affinity. It is just the attraction that an element has towards the electrons that it is sharing with other elements. We also have a graph here in your textbook of electronegativity values. They are highest up in the upper right-hand side of the periodic table. Fluorine is the most electronegative element. Down in this lower left is the least electronegative elements over here. And this is not really a measurable quantity. This is an arbitrary scale, just a ranking that was done by a scientist named Linus Pauling that just gave sort of a ranking and a rating of how much these elements pull on the electrons when they're bonded to an element of a different type, which ones pull on the electrons more. If two elements have the same electronegativity, so the difference in the electronegativity of the two elements is 0 or is very small, then those elements are pulling on the electrons evenly and we get a nonpolar covalent bond, an even sharing. If there's more of a difference in the electronegativity, we get a polar covalent bond, so this is an uneven sharing. If we have a really big difference in electronegativity and one of the elements really wants the electrons a lot more than the other element, it will pretty much take those electrons, so there will be no sharing whatsoever. It will just be an ionic bond. This is a general guide. Sometimes you do have an ionic compound, a metal and a nonmetal, like we learned before. Those are a sign that you have an ionic compound, something that can form a cation and something that can form an anion. And sometimes you have those ionic compounds even though the difference between the electronegativities on that chart is only 1.8 or 1.7. So make sure you just use this as a general guide rather than a hard and fast rule here. Another thing we're going to take a closer look at is compounds that have polyatomic ions. So there is an ionic bond in a compound that has a polyatomic ion, but within the polyatomic ion itself, there are also covalent bonds. We'll take a look at that down below. So I've written some electronegativity values over here on the side from that chart in your textbook. We already know that calcium and oxygen, we have a metal and a nonmetal, so they form an ionic bond. This is borne out in the difference in their electronegativities. It's a very significant difference over that 1.9 guideline for ionic compounds. And oxygen would be the element that is negative. Calcium would be the cation, the positive element. Carbon and bromine have a very small difference. So they're going to be sharing their electrons fairly evenly. This would be a nonpolar covalent compound or a nonpolar covalent bond. Oxygen and hydrogen have a significant difference. They will share the electrons, but rather unevenly. Oxygen is going to have the electrons more of the time. That's going to be partially negative near the oxygen and partially positive near the hydrogen because it's getting its electrons pulled away from it more. Carbon and hydrogen have a very small difference, so they are pretty even sharing. It's a nonpolar covalent bond. So molecules that have just carbon and hydrogen, this is very important when you get to organic chemistry. Hydrocarbons and molecules that have just carbon and hydrogen, or areas of a molecule that have just carbon and hydrogen, are very nonpolar, and they tend to not be very attracted to water, which is a very polar compound. So this is a very important quality in chemistry. On the other hand, carbon and oxygen are a little bit more different. This is going to be a source of polar bonds, even within organic molecules. And these polar covalent bonds have the electrons spending more time around oxygen and a little bit less time around carbon. Here we have lithium, a metal, chlorine, a nonmetal, fairly big difference in electronegativities. This is an ionic compound, or would be an ionic bond between these elements. We would have lithium as a cation and chloride as the anion. Bromine and bromine will share electrons fairly evenly because the difference between their electronegativities is 0. that covalent bond is nonpolar. I want to point out the simulations for polarity that are found in our week 10 module. So here are the shapes we're going to be talking about at the end of the chapter. And then here is one on molecule polarity. Let's take a look at two atoms. We're talking about differences in electronegativity and the polarity of the bond. So here we will turn on the partial charges. You can see the little deltas here, the bond character, whether something's more covalent or more ionic. And the negative end is more of a red color, the positive is more of a blue color. If these atoms A and B have the same electronegativity, so let's go ahead and put this in the middle, then we have a completely nonpolar covalent bond. The dipole has disappeared, the little delta negative and positive disappeared. All of the molecule here, or all of the bond, is neutral. It's kind of like this center white color. If you turn on an electric field and twist the molecule around, it does not get affected by the electric field. Let's go ahead and make a very polar bond. Let's make this one very little electronegativity and make this one a lot of electronegativity. So this is getting closer to an ionic bond. We have a lot of positive and negative charge here, a very long arrow to show that there's more of a dipole. As you increase the electronegativity, it gets longer. And then if you turn on an electric field, it is attracted to the field. If you twist the molecule and turn on the field, it's going to line up so that the negative end of the molecule is next to the positive plate. So you can play around with this and see, you can make the other atom more electronegative and have it flip around. So this is in case the playing around with it hands-on, so to speak, can help you understand what bond polarity is. Sodium and bromine, we have a metal and a nonmetal forming an ionic compound with a fairly significant difference here. We have sodium as a cation and bromine as the anion. So here is an example over here where we have a metal and a nonmetal. The difference is just a little bit shy of what we say the cutoff is, but we know that these two elements are going to form an ionic compound. We're going to have a lithium cation and a bromide anion. So there's no reason why lithium chloride and sodium bromide would be ionic and yet lithium bromide not be ionic. This is definitely an ionic compound. So even though we are looking at this a little bit more closely, don't forget what you learned before in the naming chapter, that a metal and a nonmetal, or a metal and a polyatomic ion, those are combinations that form ionic compounds. Speaking of polyatomic ions, let's take a look at these compounds that contain polyatomic ions. So we have ammonium ion as the cation, and we have chloride ion as the anion. So these are the two ions. They would go off away from each other in water. But the hydrogen and the nitrogen would not fly apart from each other because these are actually connected with covalent bonds. So we'll take a look at that structure in the next section. We have the same thing here. We have the cation, which would be calcium, and then we would have two nitrate anions. So the nitrate itself is an ion. It is dissolving and dissociating away from the calcium and away from each other when you put this into water, but the oxygens and the nitrogens are linked together with covalent bonds, so they do not come apart from each other. So this compound would separate into three different ions when you dissolve it in water. And here we have zinc sulfate, and when you dissolve it in water, it separates into a zinc cation and a sulfate anion. But the sulfate anion does not dissociate into oxygen and sulfur because these are connected by covalent bonds.